Other interesting stuff. I like talking about radiation because it's kind of fun. So who knows what this is? Yes. Okay. Last class didn't know. Nobody knew what it was. What? This is the cosmic background radiation. So if you ever want to have as close as possible model of a black body, it is the cosmic background radiation. So through these, through the different measurement devices that have been created, one of them is called COBE. They've been able to measure the intensity of the light emitted by background radiation. By the way, so what this is, if you don't know, right, this is the leftover radiation that's just bouncing around the universe from when it was first, when it first went through the transition from Big Bang to transparent. Right? At a certain moment in time, the universe had cooled enough where the gases became transparent. At that moment, radiation started bouncing around. Right? So over time, over the eons, it has cooled, and it is now roughly at the temperature, what I have a note here, it's roughly at the temperature T is equal to 2.725 plus or minus 0.002 Kelvin. So that is the temperature of the universe, right? They know it really precisely, and so you can look at this and you can compare it to the measured intensity as a function of, I guess they have it as frequency here, but looking at wavelength, right? And this COBE data, the red pluses, is measured data. Right? This is measured intensity. This blue line is the black body spectrum. So incredibly, it lines up almost perfectly. Let's actually get to stuff that is useful to you in developing models. So, okay. We need to break down light into, or radiation into kind of these three different categories. So I'm going to give you some definitions. We'll kind of go through what they are, and you'll see some distinctions. So we're talking about emitted radiation per unit area. We have, I guess, three things. So one is, we've used this word black body. So black body, spectral, emissive, power. Okay, so that is, we use the nomenclature for that, E-B lambda. The units on that are watts per micron meter squared. So the important thing to know, you'll see the contrast, but we're talking about a black body. We're talking about spectral. So spectral means we're looking at a specific wavelength, lambda. So our nomenclature says EB, black body, comma, lambda. That's a specific wavelength. And then emissive power is, of course, the E part of it. So what you see is at a given wavelength, a given micrometer, micron, you have a watts per meter squared. That's what that's telling you. You can also have spectral emissive power. Okay, so that would just be E lambda, again with the same units, watts per micron meter squared. And that is a function of wavelength, but it is basically the real, so this is like the real emitted power. So it's exactly the same as black body, except that it's not ideal, right? It's the real surface's emitted power. The last thing you could have would be the black body emissive power. Okay, that is, it is E sub B. Units on that are just watts per meter squared. So this is the integrated value of the top one. So this is the total black body emitted power over all wavelengths. Okay. Okay, so let's give a definition for that. That is emitted power. Sorry, where am I? Black body. Sorry, one slight subcategory here. Okay, so let's say we want to know the emitted power E. So E is going to be equal to the integral from 0 to lambda of E lambda d lambda. So that would be, I guess, looking at the real emitted, the real total emitted power. So this is actually emissive power. And you can do the same thing for the black body spectrum, right? You just say EB is equal to the integral of the black body, right? So, okay, we have these definitions in hand. We can use them to make evaluations. Let's see. So let's maybe sketch out just really quickly what I'm talking about here, just so we're all clear. So the first thing would be we have a black body spectrum. So let's pick some temperature. That's going to look like this. So let's say this is EB as a function of lambda. So if I have a real surface, my real surface might fail to achieve that ideal surface. And it might look something like, you could just pick a curve, but maybe it would look something like this. So this would be E lambda. That would be my real surface. Here we're plotting wavelength, and on this axis we have emissive power. So then, we're talking about here with the integral would be, looking at the integral of this area here. Okay. Okay, well, another definition here before we move on. So let's say we want to get EB. So EB would be equal to the integral from 0 to infinity. Sorry, I made a mistake up here. This should be integral from 0 to infinity. We're taking all wavelengths. Okay. Integral from 0 to infinity of EB lambda d lambda. So if we evaluate that using Planck's law, that is the integral from lambda equals 0 to infinity of this whole thing, C1 over lambda to the 5th exponential of C2 over lambda t minus 1 d lambda. And it turns out that's equal to sigma t to the 4th. Okay. If you're falling asleep, you might just have woken up. So this whole thing is, this integral here evaluates to that. Go figure. So that, if you ever want to know the total power emitted by a black surface, it's that value. That maybe looks a little bit familiar because if you're doing radiation exchange like we've done, we did like the first week of class, you're looking at the emissive power difference between two surfaces. So you're taking sigma t 1 to the 4th minus sigma t 2 to the 4th. So that's where that comes from, that t to the 4th. It's just the integral of this thing here. And again, sigma is equal to 5.67 times 10 to the minus 8th. And the units are watts per meter squared, Kelvin to the 4th. That's the Stefan Boltzmann constant. Okay, so we've got some definitions. We kind of have an understanding. Again, we know a surface can emit a power. Ideally, it can actually emit a real curve like you see here. So then the question is, okay, how do we actually evaluate the power that's emitted by a surface in circumstances like, say, we want to know the power that's emitted from one wavelength to another?